Let's prove the following algebraic properties of matrices using the given three matrices A, B, and C and scalar quantity A and B. So these properties are actually true, and we are to prove show a proof using the given matrices. The first one is the associative law for matrix addition, where we're going to add first B and C on the left hand side and add A later. Will be the same as when we add A and B first before C. Take note that our matrices here are all 2 by 2 matrices, so they are all defined in terms of addition, and they're also defined in terms of multiplication, as it's also the concern a little bit later. So let's start first with B plus C here, and later we also have A plus B on the right hand side before we subject to the remaining matrix. When we add, we simply add the entries. So for B plus C, 0 plus 4, 4, 2 plus 1, 3, 1 plus negative 3, negative 2, negative 4 plus negative 2 is negative 6. That's for B plus C. For A plus B, same thing here. 3 plus 0, 3, negative 1 plus 2 is positive 1, 2 plus 1, 3, 4 plus negative 4, 0 here. Now we are to show that the resulting matrices on both sides will be the same if we are going now to add the remaining. So A plus B plus C. So we simply add all entries of A to this result here. So 3 plus 4, 7. Negative 1 plus 3 is 2. 2 plus negative 2, 0. And then 4 plus negative 6, negative 2. Is it the same as when we are going to add the remaining matrix C to our previous answer? So add all of this to C here. So you have 3 plus 4, 7. 1 plus 1, 2. 3 plus negative 3, 0. 0 plus negative 2, negative 2. As you can see, both results are just the same, and this means the associative property or associative law for matrix addition holds. Next is for associative law for matrix multiplication. But since it's a multiplication, please follow the concepts or the process for multiplication. But of course, we are sure that the results are defined since all matrices here are 2 by 2. So let's have B times C first, meaning you multiply the row of B to the first row of C. 0 times 4 is 0, and then the second will have negative 6. That's 2 times negative 3. Next, multiply the same row here. So 0 times 1 is for 0. 2 times negative 2, I have negative 4. Next, this row here will be multiplied to the same columns. So 1 times 4 is 4. Negative 4 times negative 3 is positive 12 rather. 4 plus 12, I'm sure to have 16. And then 1 times 1 is 1. Negative 4 times negative 2 is positive 8. 1 plus 8, I have here 9. Okay. So I need to multiply that to A later. Or my handwriting is a little bit bigger. I hope that it will have enough spaces. So let's start with AB first in this area. So same thing, but it's the row now of A against the column of B. 3 times 0 is 0. Negative 1 times 1 is negative 1. Next, the same row to this column here. So 3 times 2 is 6. Negative 1 times negative 4 is positive 4. 6 plus 4, 10. Next, the second row to this column. 2 times 4, 0 is 0. 4 times 1 is 4. So you have here 4. Then 2 times 2 is 4. 4 times negative 4 is negative 16. I have 4. I have negative 16. I have negative 12 remaining. And we're going to multiply this to our C. But take note of the arrangement, okay? It should be AB first before C. In short, the rows of AB versus the columns of C. On the other side, notice that it's A times BC. So it's the row of A times the column of B. That disarrange the process. So I have here again the row of A. 3 times negative 6 is negative 18. Then negative 1 times 16 is negative 16. Again. Yeah. So I have negative 3 times negative 6 is negative 18, right? Then I have negative 16, so that's negative 34. Negative 34, right? The same row against here. 3 times 2 is 6. Then negative 1 times negative 4 is, my bad. It's this one here. It's this row against this column pala. So 3 times negative 4 is negative 12. And then I have negative 1 and 9. I have negative 9. Negative 12, negative 9. I have negative 21. Next, this row against here. So 2 times negative 6 is negative 12. I have 4 times 16 is 64. So negative 12. I have 64. So I have positive 52. Then I have here as well. Here, 2 times negative 4 is negative 8. 4 times 9 is 36. And I have negative 8. So I expect to remain in 28. So this should have the same results when we deal with the second. So it should be this row against the column of C. Okay? So negative 1 times 4 is negative 1. And then 10 times negative 3 is negative 30. Negative 4, negative 30, negative 34. See, the first entry is already the same. Hopefully the rest would be the same as well. So I have the same row here, and I'm going to multiply that to the next column. Negative 1 times 1 is negative 1, and then 10 times negative 2 is negative 20, negative 1, negative 20, negative 21. See, the results are just the same. Next, I have the next row here times this one. So I have 4 times 4 is 16. Negative 12 and negative 3 is negative 36. Negative 36, positive 36 and 16 will result to 52. So we have 52 here as well. And then, last one. 4 times 1 is 4. And then, negative 12 and negative 2 is positive 24. 4, positive 24. So you have 28. See, the two results are just the same. This means the associative law for matrix multiplication also holds. The next property is actually a left distributive law. So we are going to start first with the addition of B and C, but it's already here. Check this one here. That's already B and C. So I can multiply A to B and C, because again, I have here the results already. So I'm going to use this row against this column of B and C. 3 times 4, pardon again if a portion of the previous examples would be highlighted. So 3 times 4 is 12, negative 1 and negative 2 is positive 2, 12 and then 2. Here I have 14. Next, the same row against here. 3 times 3 is 9. Negative 1 and negative 6 is positive 6. 9 times 6, 15. Next, the bottom row, second row against here. 2 times 4 is 8. 4 times negative 2 is negative 8. 8, negative 8, 0. And finally, for this first part, 2 times 3 is 6. 4 times negative 6 is negative 24. Positive 6, negative 24, I have negative 18. This is for the entire left-hand side of the left distributive law. Now we are going to add AB and AC. But AB, if I'm correct, please look into this one. This is already AB. So I am sure to already have AB in the form of -1, 10, 4, and -12. I'm going to add it to AC, but I don't have AC yet. So I'm going to make AC here. AC means the row of A against the column of C. So 3 times 4 is 12. -1, -3 is +3. 12 and 3, I have 15 here. Okay. Next, the same row for A, but second column for C. 3 times 1 is 3, -1 and -2 is 2, 3 and 2, I have here 5. Next, the second row of A, 2 and 4 against this. 2 times 4 is 8, 4 times -3 is -12, 8, -12, I have 8, -12, I have -4. And finally, for the last second row and second column, 2 times 1 is 2, 4 and -2 is -8. 2, -8, I have here -6. So if I'm going to add AB and AC, so -1 and 15, that's 14. 10 and 5, 15. 4 and -4, 0. 12 and -12 rather, and -6 is -18. See? They have the same results, therefore, the left distributive property also holds. The remaining property here is about scalar quantity A and B. Still distributive property, but with respect to the scalar quantity. So it states here that if we are going to add A and B before multiplying it to C, it's just the same as multiplying both scalar quantity to the same C or matrix C. AB here is 4 and 7. So A is 4, B is 7. So A plus B is equal to 11. So I have AB, sorry, that's 11, my bad, 11. So I have A plus B times C is equal to 11C. So simply multiply 11 to all the items, or the entries rather, of C. So let me add here the C. Okay. C is 4, -3, 1, -2. So times 11, so positive 44, positive 11, -33, -22. It should be the same, or it should have the same result as this. So let's try to get AC first. AC meaning multiply 4 to all the entries here. So you have 16, 4, -12, -8. BC as well, sorry, that's a capital C because it's a matrix C. Is we multiply 7 to all the entries here. So you have 28. I have the next one, which is 7, -21, -14. When we add these two, they must result to this item here. So let's try to check. AC, again, pardon, it should be capital C, plus BC is this one. 16 plus 28 is 44. 4 plus 7, 11. -12, -21, -33, 8, and then -14 is -22. As you can see, they have the same results as well. This means that this distributive law, or property, pardon, is also true. So we have proven the first 4 algebraic property of matrices using these given matrices and scalar quantities A and B. So this means, again, associative law for addition, associative law for multiplication, the left distributive property, and this property with scalar quantity are true for all matrices. Thank you for watching.